A tower stands in the desert sun. Its shadow stretches 173 feet across the sand. Without climbing the tower, how could an ancient astronomer know the sun's angle just from this shadow? Thousands of years ago, civilizations had no modern tools. Yet they predicted eclipses and tracked planets. Their secret was hidden in a simple triangle. We just saw a shadow measure the stars. That ancient trick is the heart of trigonometry. The word itself tells you exactly what it is: triangle measurement. If you know one sharp angle inside a right triangle, you instantly know the ratios of all its sides. It is a lookup table built into the shape of the universe. These three ratios are the main characters. Sine, from the Latin sinus, a meaning a bay or curve. Cosine, its companion. And tangent, the line that just touches the circle. We just saw what trigonometry is, but why did anyone need it? Imagine being a farmer for 1,000 years ago. You can't just check a phone for the planting date. But you notice the same stars return to the same spot in. Now, take that problem to the open ocean. With no landmarks, sailors were blind. But they realized the North Star's height above the horizon, an angle, never changed for a given location. Measuring that angle with a simple tool gave. We just saw why measuring the sky mattered. Now, let's see how they did it. The horizon gave them a natural starting line, a flat zero. From there, they imagined a quarter circle stretching straight up to the point directly overhead. A person pointing at a star creates an angle. Their arm becomes a moving radius, sweeping up from the flat horizon. The height of that star is simply the angle between the horizon and their arm. The sun's steady march across the sky turned angles into a clock. It climbs 15 degrees every hour. By tracking the sun's highest point at noon, its angle, ancient people could predict the seasons, the Nile's flood, and the time. We just saw how shadows track time. Now, to measure the sky, we need a way to describe direction. An angle is simply the spread between two lines that meet at a point. Imagine a door. When it's closed, the two lines, the door and the frame, have no spread. As you push it open, the spread grows. That growing spread is the angle. In the sky, we use the same idea. One line is the flat horizon. The other points to a star. The angle between them tells us exactly how high the star sits above. We just learned an angle measures spread. Now, to measure a full turn, like the sun's daily path, we need a full circle. The Babylonians divided that circle into 360 parts we call degrees. Why 360? Start with a circle's radius. Walk it around the edge, it fits exactly 6 times, making 6 equilateral triangles. Since each triangle's corner is 60 degrees, 6 of them give 360. The Babylonians counted in 60s, using finger joints, not just fingers. 60 divides cleanly by 2, 3, 4, 5, and 6. By choosing 360, they baked that easy divisibility right into the circle. This 360 fits the sky beautifully. The sun shifts about 1 degree eastward each day against the stars. After roughly 360 days, it completes its yearly loop, turning the circle into a cosmic calendar. We just built the circle with its radius. Now, instead of a line from the center, draw a straight line connecting any 2 points on the edge. That is a chord, and its length depends entirely on the angle it opens. Watch what happens as the angle grows. At 60 degrees, the chord is exactly as long as the radius, forming an equilateral triangle you already know. At 180 degrees, the chord stretches across the whole circle, becoming the diameter. Greek astronomers turned this into a powerful lookup table. For any central angle, they recorded the chord length, a direct ancestor of the sine function. Next, we will see how this chord evolved into the half chord we use today. We just saw how a chord works for one angle. But measuring the sky means countless angles. Drawing each one from scratch is impossibly slow. Hipparchus needed a shortcut, a way to look up any chord instantly. On the island of Rhodes, Hipparchus used a diopter, a rotating sighting tube on a graduated circle. He'd aim it at a star, read the angle from the horizon, then calculate the chord that matched that slice of the sky. He set his circle's radius to 60, a clean base, a 60 number. Then, starting from special cases like the 60 degrees chord equaling the radius, he used geometry to fill in other angles. The result, the first table of chords, a lookup list. We just saw Hipparchus use the full chord across the circle. But notice, every chord calculation forces you to work with the whole central angle. What if we only needed half? Around 500 CE, Indian mathematician Aryabhata drew a vertical line from the midpoint of the arc straight down to the horizontal diameter. He called it Uadajaya, literally half chord. Look how it forms a right triangle inside the circle. The full chord needed the whole isosceles triangle, 2 equal sides. The half chord gives you just one right triangle. Now you can directly compare the half chord to the radius as a simple ratio. This ratio works for any circle, big or small. We just built the half chord inside a circle. Now step outside, plant a vertical stick in the ground. As the sun climbs, its shadow shrinks. The ratio of stick to shadow gives us a new way to measure angles, without any. Divide the stick height by the shadow length. When the sun is at 45 degrees, the shadow equals the stick, so the ratio is exactly 1. As the sun sinks lower, the shadow stretches longer, and this ratio grows rapidly. Flip the fraction, shadow length divided by stick height. This is the cotangent, the complementary tangent. It's huge when the sun is high and tiny near sunset. Together, tangent and cotangent gave ancient astronomers a complete shadow table for any altitude. We just saw how a simple stick's shadow gave us tangent and cotangent. But to fully map the heavens, scholars needed a complete set of tools, a function for every ratio in a right triangle. In Baghdad, Al-Khwarizmi and Al-Battani didn't just gaze at stars. They built precise observatories, using giant astrolabes to measure angles, then spent years recalculating tables to fix errors from ancient Greek charts. Looking deeper at the shadow triangle, they isolated a new ratio, the hypotenuse divided by the shadow's base. This cutting line across the circle became the secant, completing the toolkit for precise astronomical. We just saw the Islamic Golden Age polish the cosmic mirror. Now, these Arabic manuscripts travel to medieval Europe through Spain. Translators turned the JB into the Latin sinus, meaning bay or curve, giving us our word a sine. This math was about to. Out on the open ocean, a ship's captain needed one crucial number, latitude. The pole star hangs almost perfectly above the Earth's north pole. So, if you measure its angle above your horizon, that angle is your latitude. A simple tool called. A sailor would sight the pole star along the quadrant's straight edge. A weight on a string, a plumb line, hangs perfectly vertical, pulled by gravity. Where that string crosses the curved degree scale, it marks the star's altitude, your latitude, using the same. We just saw trigonometry travel to Europe. Now watch it scale up. Surveyors started with just one precisely measured baseline on flat ground, then used angles to leapfrog across an entire continent. To measure those angles across mountains, surveyors used a theodolite. Its telescope swivels on a finely engraved circle, letting them read the spread between two distant towers in degrees, minutes, and seconds. From a solved triangle, one side becomes the known base for the next. Tower by tower, the survey stitched a web of triangles across India, even measuring the height of Mount Everest with nothing but angles and a single starting line. We just measured a static continent. Now, set that triangle in motion. Imagine a point traveling around a circle at a steady speed. Its height above the center traces a rhythm over time. Now, unroll that circular motion. As time moves forward, the point's changing height draws a smooth, repeating wave, the sine function. It turns a static table of angles into a living shape. This same wave shape appears everywhere: a vibrating guitar string, a ripple of light, even radio signals. The ancient half-chord grew into the universal language of oscillation. We just saw how surveyors mapped continents with ground-based triangles. Now, we flip the script. The known points are satellites whizzing overhead, and your phone becomes the unknown vertex. A GPS satellite constantly broadcasts its position and the precise time. Your phone compares the signal's arrival time to when it was sent. Multiplying that tiny delay by the speed of light gives the distance to that satellite. Knowing you're, say, 20,000 kilometers from one satellite doesn't give your exact spot. It just means you could be anywhere on the surface of a giant imaginary sphere, with that satellite at its core. Add a second satellite, and its distant sphere intersects the first. Their overlap forms a circle. A third satellite sphere cuts that circle in just 2 points. One is in space, the other is you on Earth, solving the cosmic triangle. We just saw GPS triangulate your position. That journey began 4,000 years ago. Babylonians drew circles and divided them into 360 degrees. Hipparchus then measured the sky with chords. Indian mathematicians later halved that chord, giving birth to the sign. Islamic scholars polished these tools, adding tangent and building precise astrolabes. Centuries later, surveyors used triangulation to measure continents. Finally, the sign became a pure function, a wave that describes any oscillation. Now, look up. The same geometry that charted stars now guides satellites. Your phone listens to their signals, solving a sphere intersection problem with trigonometry. The ancient circle has become your personal cosmic ruler. We just saw how a chord becomes a sign. Now, a sailor measures a star's angle above the horizon. Using that angle and a sine table, they find their latitude, their distance from the equator. Back on land, to find a mountain's height, walk 100 meters from its base. Measure the angle up to the peak. At 45 degrees, the tangent is 1, so the height equals your distance, 100 meters. We've traveled from clay tablets to GPS. The single most common slip-up is swapping sine and cosine. Just picture the unit circle. At 0 degrees, the height is 0, so sine is 0. The shadow on the ground is full length, so cosine. To lock this in forever, use the ancient chant, SOHCAHTOA. It spells out the ratios. Sine is the opposite side over the hypotenuse. Cosine is the adjacent side over the hypotenuse. This simple phrase is your mental anchor. You just learned the theory. Now, become an ancient astronomer. Push a stick straight into the ground. Measure its height and the length of its shadow. Divide the shadow by the height. You've just calculated the cotangent of